Chemistry, this is the review video for the week 13 quiz. It was given out on Monday, November the 4th. So percent composition by mass. We did that with solutions. This is with solids, so it's the same thing. So let's do this. Calculate the molar mass. Okay, and it's 92.02 grams per mole for N2O4. Now you simply take these one at a time. So for O, it's going to be this. Excuse me, for nitrogen. Let me correct that. Okay, and you simply do that. And for this, I'm going to write it down here. It's 30.04%. I really don't care how many places after the decimal. Okay, that's not a big issue. Okay, and for O, and that's going to give us 69.6. So the percent composition is 30.4% for nitrogen, 69.6 for oxygen. If two compounds have the same percent composition from mass, then they have the same empirical formula. Okay, next up, a compound is determined to be 43.6% phosphorus, the remainder oxygen. What is the empirical formula? So empirical formula must be in moles, not in grams. But first we convert the percent of phosphorus to grams. So convert percentage to grams. So come down here first for phosphorus and then to moles. And go to the periodic table, which says phosphorus, number 15 is 30.97 grams per mole. So your conversion is to put grams on the bottom. This cancels, and that gives you, I'm going to put 1.4. You want to reduce the number of digits on empirical formulas because you need to come out with a ratio. Remember, so you'll see that in a minute. So oxygen, we're going to say is the remainder is oxygen. So 100 minus 43.6 will give you the percentage of oxygen, which is 56.4 grams. So they have to add up to 100 because it's a percentage. And we know the molar mass of oxygen from the periodic table. 16 grams. It's not an O2, it's just an oxygen atom. Okay, and it gives me 3.525. I'm just going to call it 3.5. And that's moles of oxygen. And this over here should be moles of phosphorus. So now we're going to drop all the units of measure and we're just going to make ratios. So for phosphorus, smaller number on the bottom. For oxygen, smaller number on the bottom. And that gives you 2.5. So we've seen that relationship before. So you got to get this to be a whole number. You multiply it by, keep multiplying by integers until you get there. So you're going to multiply 2.5 times 2 gives you 5. you got to also multiply the 1 by 2. You got to keep the ratio between them the same. So what you're going to end up with is empirical formula of P2. So this is oxygen, this is phosphorus. Always keep labeling them, otherwise you can get them backwards. So it's P2O5 is the answer. Okay, next up we have this one. Back it off a little. Okay, 12 grams of carbon, 3 grams of hydrogen, 8 grams of oxygen. What's the empirical formula? Okay, so they're giving you nice round numbers, so just round off. So for carbon, the molar mass is 12. If you round it, 12.01 to 12. So we're going to figure the molar mass. Now, some of you that are developing some sophistication, I think you all are, the molar mass from the periodic table is 12.01. We're going to call it 12. You could just do 12 over 12. You don't have to do this whole conversion factor because you're going to be doing a lot of these, and that's going to be a 1 mole. Then we go to hydrogen. We're just going to call that 1. Whoops, it's 3 grams here. Grams cancels, and 3 moles. And finally, oxygen is 8 grams. And it's 16. We're dealing with a single oxygen atom. And that's going to be 1/2, 0.5. So I'm going to drop the units of measure. You don't need to use them. So carbon, the smallest number is 0.5. 1 mole there, 3 moles there, 0.5 moles. So for carbon, hydrogen is 3 moles over 0.5. And oxygen, which equals 6 to that, and oxygen is 0.5 over 0.5. Okay, so it's going to be C2H6O1. You can't reduce that. If you could reduce that, if for example this was a 2, you could have reduced it down to 6,2. You could have reduced that, but you can't here. So it's going to be C2H6O. Okay, and that'll be your answer for that. What does anhydrous mean? No water. Or without water would be a better way to say it. Okay, without water, it's hydrous molecules are molecules that even though they're dry, they have water molecules attached to them. They're not liquid, they're solids, but they have water molecules attached. Okay, we are going to go to the next page. Okay, when a 3.22 gram sample of an unknown hydrate of sodium sulfate, the unknown is you don't know what the X is. So there's the formula, but you don't know what that coefficient is for water. It says when it's heated, the water's driven off. It evaporates, basically. The mass of the anhydrous sodium sulfate, molar mass, 142, that remains at 1.42 grams. So what's the value of X? You're trying to find X. So here's the way you do, I think you should do this, is write out this formula. And the dot just means you're going to have that many times water molecules on it, okay? So first of all, you want to break it apart in grams. And then go to moles, because empirical formulas are always in moles. Any chemical formula is. So what I'm going to do is say that these two equal 3.22 grams. That's what they say the weight of the sample is. And they say when the water's driven off, the mass of the anhydrous sulfate is 1.42. So that's this right here, the NaSO4. Okay. And this is a question mark. We don't know what this is, but we know that this is 142. The total thing is 322. So you subtract those two. So the mass of the water, the XH2O, is 3.22 minus 1.42, and you get 1.8 grams of H2O. Okay, so now you know this, and you know the mass of the sample. So now you got to get an empirical formula for that, and so that means the mass of the we know the mass of all three. Okay, so first we're going to get molar masses. So molar mass, I'll write it way up here, get it out of the way. For NaSO4 is going to equal 118.4. Again, you know how to do this. Grams per mole. And for H2O molar mass, you already know that. And that's going to equal 18.02 grams per mole. Okay, so now we're going to figure out how many moles of each of these we have. We have 1.42 grams of NaSO4. Now I'm going to start using the shortcut. Instead of writing times 1 mole over 118, I'm just going to put it over this. Okay, so a little bit of a shortcut. Before I was writing 1 mole over 18.04. I'm going to go ahead and write it like that. And that's going to give us, and for H2O, and we said that there's 1.8 grams over 18.02, so they're trying to make that easy. 1.8 grams over 18.02. I'm just going to call it 18 because you can see what they're trying to do. They're trying to give you a simple number, 0.01. Okay, and with this one they're probably trying to give us a simple number, 0.001. So I'm going to erase that. You don't have to if you don't feel comfortable, but again, we're trying to get ratios in empirical formula. So for Na2SO4, the smaller number on the bottom, and for H2O, and that's going to equal 10. So for every 1 mole of Na2SO4, we have 10 moles of water. So you have 1 mole in this formula right here, 1 mole Na2SO4, so X is going to be 10. Again, if you like to write the coefficient of 1, go ahead and do that. 1 mole of that, 10 moles of that. So X equals 10. All right, so 10 H2O. Compound that contains only CH and N is burned completely in O2 to produce 44 grams of CO2. So certain molar masses you should end up having memorized. If you calculate it, CO2 is 44.01, so we're just simply going to say this: 44 grams of CO2. And again, instead of writing 1 mole over 44.01, first of all, I'm going to make it 44. I'm just going to put it down here on the bottom. 44 grams per mole. If you cancel grams, the moles flip up to the top and you end up with 1 mole of CO2. Okay. All right. Now, this empirical formula is going to be interested not in CO2. So it's a CO2. It's interested in carbon. So for every 1 mole, again, be sure you're comfortable with this. For every 1 mole of C1O2, that's what it means, you have 1 mole of carbon for every 1 mole of CO2. So we're going to just write that, go ahead and write that right here, 1 mole of carbon. Again, there's 1 C for every 1 CO2. There's 1 bicycle seat for every 1 bicycle. Okay, now we're going to go over to H. And they say we have 45 grams of H2O rather. Okay, so for H2O, we have 45 grams, and the molar mass of H2O, we're going to go to round numbers, it's 18.02, we're going to call it 18. And that equals 2.5. But we're not interested in H2O. We're interested in H. So for every 1 mole of H, again, let's write this out like this. For every 1 mole of H2O, we have 2 moles of hydrogen, and that's what we're interested in. So this is 2.5 moles of H2O. So that means we have twice that many moles of hydrogen, 2 for every 1. Okay, so that's 5 moles of H. Okay, so right there, you see that. 1 mole of C, 5 moles of H. Now what about N? They didn't tell us anything about N. Good news is, it's a multiple choice question, you don't need it. You're going to have 5 moles of H for every 1 mole of carbon. So where do we see that? We see that right here is B. 1 mole of carbon, 5 moles of H. So that's going to be the answer. All right, what is a mixture? Okay, so a mixture is, it's 2 or more separated substances. They're not bonding together. So if you put sugar and salt in the same bowl, that's a mixture. They're not bonding together in any way, but they're in the same place. Okay, so they're separate substances. Okay, identify the following as element or compound. Here's what I'd like you to do. Okay, well, an element. Individual dots, this is a particulate diagram, would be elements. Okay, so A is both. Okay, it's element, I'll just abbreviate that, and compound for A. Those are compounds. That would be like an O2 molecule, for example. Okay, over here, you have them mixed together, or they combined to create, this is not a mixture, this is a chemical reaction, and you ended up with this. So that's a compound entirely. Okay, this is element. Even though it's a molecule, because there's 2 of them, it's like O2 or H2, they're still elemental. And this is both. Just write both this time. Okay, all right. And is it a mixture or a substance? So this would be, so let's go back to the first one. This would be a mixture. This would be pure substance. So you say, but it's made of 2 different elements, it looks like. That's still a pure substance. Water, if you have just water, that's H2O, but that's a pure substance. Okay. Then down here, it's element, and then down here, it's a mixture. Okay. Okay, a 2.4 gram sample of a mixture of calcium chloride and sodium chloride is found to contain 0.12 grams of sodium. What is the percent of this sample's NaCl? So percent always means by mass. So it means it's in grams. But this one's a little involved. You're going to have to convert to moles to figure out how many grams of Cl you have. So you know you have 1 mole of Na for every 1 mole of Cl. So let's figure out how many moles of Na we have, and we'll know that we have the same number of moles of Cl because it's a 1 and a 1 on the subscripts here, okay? So I'm going to come down here, 0.12 grams of Na. Okay, and I'll go ahead and write my formal stoichiometry this time, not shortcut. You can shortcut it if you want. Just put the molar mass of Na, which is 22.99 from the periodic table, grams per mole, and that's going to give you moles. So you could have just put 0.12 over this if you want a shortcut like that. You can do that. All right, and what does that give us? 0.05 moles of Na, and that means we also have 0.005 moles of Cl. Again, the chemical formula says there's 1 Na for every 1 Cl. It's a 1-to-1. So now what we want to do is figure out how many grams of Cl that is, okay? And I may have to end up working up here just to let you know, because I didn't give you a lot of space to do this. So we know we have 0.2 0.12 grams of Na. So we multiply this by the molar mass of chlorine, which is 35.45. Remember, eventually we want to get back to grams, okay, because percent means percent by mass. Okay, and that's over 1 mole, okay, of chlorine, and that's going to equal 0.185, I'll call it 19. And I don't want to go too many places, and that's grams of Cl. So now we know our grams of Na and our grams of Cl. So we're going to add those together to get the grams of NaCl. And actually, I'm going to make this 0.2. I'm just going to simplify it a little bit. No, I shouldn't do that. It's 0.18. No, I'll stick with 0.9. Okay, so it's 0.12 grams of Na. Okay, plus, so that's, I got that right there, plus what I figured out I had grams of Cl. Okay, we add those together and we get 0.31 grams of NaCl. Okay, so that's how many grams of NaCl. Now it says the mixture of the NaCl and the CaCl is 2.4 grams. So let's go ahead and break that down and figure out how many grams of CaCl we have. Okay, so we have 2.4 grams of both. I'm just going to call it both. It's the CaCl and the NaCl. Okay, this problem's a little involved, but you practice these, you get good at them. Anything you practice, you'll get good at. Minus the 0.31 grams of NaCl. And what you're going to get from that is 2.09 grams of CaCl. Okay. Okay, so we figured out grams of NaCl. We don't care about CaCl because the question is asking us percent of the sample is NaCl. So again, mass percent, whenever you see percent, it means mass, it means grams. So we have 0.31 grams of NaCl and 2.4 grams of the sample. So although I computed the grams of CaCl, we don't care. I'm just going to write don't care. So you didn't need to do that step, so you can skip that. So here we go. So to get the mass percent, it's 0. From this calculation, divided by the grams of the sample. Sample. And again, sample means both of them together. Okay? And if you do the math times 100%, you get 13%. And that's the answer. Okay? Again, you didn't need to do this step. I just calculated one step beyond what I needed. Okay. Which is more important on the AP exam, explaining the lesser ionization energy to remove a valence electron? Say, why is it less from lithium than it is from chlorine? And the answer is distance. It's distance, not shielding. You could say shielding, but that's not what they want to hear. Okay, so Coulomb's law says that the force between the proton and the neutron, this sign means is proportional to, should have drawn it more like that. Let me draw that a little better. Is proportional to Q1, that's the charge of the proton, Q2, the charge of the electron over the distance squared. Sometimes they use an R instead of a D. So there's nothing about shielding in that formula. So they always want you to state it in terms of Coulomb's law. Okay, so it's distance is the answer they want to hear. Okay, here we go. All right, so look at the diagram below. Which electron, A, B, or C, is the easiest to remove? So this is a really strong charge, 2 protons pulling on 1 electron, and the electron is close. So strong charge compared to the other 2. Short distance. This is weaker charge. This one is weaker charge than A. Same distance. Okay, and this is weaker than A and longer distance. That means the coulombic attractions are going to be less. And think of it, if you're 1 billion miles away from the Earth, you're not going to feel any gravitational pull from the Earth just based on how far away you are. So longer distance. So this is strong. It's strongest. This one is weakest. And B is in the middle. So the answer is this. Okay? All right. Formal charge for HCN. So we've done that 1,000 times. First you got to draw the Lewis dot structure. So H is 1 times 1. C is 1 times 4. N. And you built models of this. It's a triple bond. Okay. So H, the formal charge, is always 0. It's always 0. Okay, C, it's going to be 4 valence electrons for C, minus lone pairs. There are no lone pairs on the carbon, minus half of the bonding, which is 8, and that equals 0. Okay, and finally N. You start with 5, you subtract lone pairs, there's 1, 2 lone pair electrons, minus half of the bonding, which is 1, 2, 3, 4, 5, 6, and that equals 0. So that's a very stable molecule. Okay, I'm going to wrap this video up and continue on a different video. Because this one's already at about 30 minutes, so I'll wrap this up.